Okay, we're going to continue on here. And as we were talking about there after the quiz for that short little bit of warm up lecture, I suppose, we talked about, again, a couple of other things that can affect the solubility of a compound. And again, those are the three sort of major things that really can affect the solubility, as we talked about. Again, concentration, pH, and the presence of a common ion all will have an effect on the solubility. And we're going to now talk about another sort of aspect of KSP that's really helpful. And although we don't, again, do these type of experiments anymore here, which are qualitative analysis type of experiments, and qualitative analysis type experiments are experiments where essentially you have a bunch of ions floating around in the solution. And basically, your goal in these type of experiments, for example, is to figure out, which ions are present. And to do that, it's a very common procedure to add some type of reagent that will essentially precipitate out one of the ions while perhaps leaving the other one still floating around in the solution. And this is what is sometimes referred to as selective precipitation, where you just want to precipitate out one ion or a certain number of ions, but leave the other one still floating around in the solution. Now, to do this, we could actually use KSP to help us figure out how to properly do that. So let's take a look at this example here together and talk about how we could use KSP to help us do that. So in this case, we want to know what concentration of silver would be required to precipitate out silver bromide from a solution that contains bromide ions and chloride ions at a concentration of 0.02 molar. So essentially what we have, maybe just steal this picture here. Maybe you'll get rid of it. Steal that here. Go. So essentially, we have a beaker, and what we have in it in this problem is we have a couple of ions in this case. We have bromide and we have chloride floating around basically in the solution. Now we're going to use silver as our precipitating reagent to dump in there. And as you hopefully know from solubility rules, silver will precipitate out both bromide and chloride as silver chloride and silver bromide. And when you do that, you will get both of these guys precipitating out. Now, the problem is if you are not really careful on how you do it, you could precipitate out both of them at the same time. And this is actually pictures of both of them. They're both basically kind of like a whitish sort of solid. And if you were interested in just precipitating out one ion at a time and not the other, you would have really no way if you weren't careful to know like which sort of solid is the chloride and which solid is the bromide. You can't just like pick through the solid and go, I think this one looks like the chloride and this one looks like the bromide. So the goal here in this question is to precipitate out our bromide out of solution and still leave our chloride still floating around, having a nice time and a nice swim. So we could look at our two sort of equilibriums that would be set up, and we would have our silver bromide that can precipitate out and will make silver ions and bromide ions. We could also have our silver chloride that will make silver ions and chloride ions. We can have our KSP for our silver bromide at 7.7 times 10 to the minus 13, and our KSP for our silver chloride of 1.6 times 10 to the minus 10. Those obviously can be found on the table. If we look at our KSP expression here for silver bromide, it would be the silver ion times the bromide ion, and that would equal our 7.7 times 10 to the minus 13 in this case. What we do know about our two ions that are floating around in the solution is we do know their concentration is 0.02 molar. So we can, in this particular case, actually use the KSP expression to figure out what concentration of silver we would need to actually see a precipitate form. So if I rearrange the KSP expression, actually just solve for silver concentration, that would equal 7.7 times 10 to the minus 13 divided by my bromide's concentration. And once again, I already know my bromide's concentration is 0.02. So putting my numbers in gives me 7.7 times 10 to the minus 13 divided by 0.02 molar. And if I do that there, we're going to get, if I punch it in right, we'll get a number maybe 0.02. We're going to get something like, we'll call it, go below, 3.9 times 10 to the minus 11 molar. So what does this number basically represent? This number represents the minimum amount of silver that you would need to add to this beaker to start to see silver bromide starting to precipitate out. So that is what that number represents. You got to at least have that much concentration of silver to start to see this guy precipitate out as a solid in this particular case. Any questions on that there? We could then do really the same calculation here for our silver chloride to figure out what is the actual concentration we need of silver to see the chloride precipitate out. So we again can use our KSP expression to help us with that. Again, that's going to be the silver and the chloride going to equal 1.6 times 10 to the minus 10. Once again, here we could solve for silver, and that would give us our KSP divided by our chloride concentration in this case. And once again, in this case, it happens to be the same molarity. So we'll pop our number in there, 1.6 times 10 to the minus 10 divided by 0.02 molar, going to get us here. Too many zeros to write at this hour. Something like 8.0 times 10 to the minus 9 molar in this case. So what does that number represent? That number represents the amount of silver that's needed for you to actually start seeing silver chloride precipitating out. So in this problem, if we wanted to just precipitate out the silver bromide without precipitating any chloride, we would need to have a minimum concentration of silver of 3.9 times 10 to the minus 11. And we would need to, in this example, keep the silver concentration below 8 times 10 to the minus 9 molar. And that will basically precipitate out only the bromide. So if you were actually doing this and you got your silver concentration to 3.9 times 10 to the minus 11, you should start seeing solid coming out of that beaker. And you can feel pretty confident at that level that the solid you're seeing is just the bromide coming out, because it is not big enough to get the chloride to come out. Again, this concentration is larger than this concentration. Now you could keep increasing the silver concentration, and as long as you keep it under 8 times 10 to the minus 9, you will continue to see precipitate come out. And that precipitate, once again, you can feel very confident is the bromide precipitating out. At some point, you may stop seeing solid come out. Maybe you precipitated most of all of it out. At that point, what you could do is, once you've got all the bromide separated out, you could centrifuge it, pour off the liquid, and then you could actually increase your silver concentration to 8 times 10 to the minus 9 or higher. And you should again start to see precipitate form. And at this point, you should be confident that the precipitate you're seeing is actually the chloride now precipitating out, because we now have the correct concentration of silver to make that happen. So this is what is sort of known as selective precipitation. You can use the KSP expression to figure out the minimum concentration, for example, of a precipitating reagent that is necessary. First off, any questions on that there? Yeah. That's the minimum concentration of silver that you would need in your beaker that has basically bromide and chloride. that would be the minimum concentration of silver that you would need to add that would be enough to start to precipitate out just the bromide. And this number here, which is 8 times 10 to the minus 9, tells us that is not enough concentration to precipitate out the chloride. So if you just wanted to, in this particular case, like the question asked, just take out the bromide, you need to at least 3.9 times 10 to the minus 11 in terms of the concentration of silver to actually start to see it precipitate. You need to keep the silver less than this number because otherwise you'll start precipitating out the chloride. And any solid that comes out with that silver concentration within that range should be the bromide basically coming out of solution at this point. Now, what would happen, for example, if I was not very careful and I just grabbed some silver that is larger than 8 times 10 to the minus 9 and I just added it in here? What would happen at that point? That is enough for everybody to precipitate out. So everybody would start precipitating out at the same time. Again, you'll get this situation here where you won't know which one is which. And obviously that's not helpful if you're trying to do it selectively. Any questions on that? Now, why in this question did they say they wanted to precipitate out the silver bromide and not the silver chloride first? Could you precipitate out the silver chloride first? You could not, because the silver bromide needs a much smaller silver concentration than the silver chloride. So there's no way to do that without taking out, obviously, the bromide with it. I should know in this case, based on KSP, which one should be more soluble, because I could actually use the KSP in this case because they both break apart into 2 ions. I could compare the KSP values that were given to us, and we could see that the KSP value for silver chloride is actually larger than the silver bromide's concentration. And because the silver chloride is larger, that means it should be more soluble, have more products than the silver bromide in this particular case. So this is actually a case where we could actually use the KSP values to predict which one should precipitate out first and which one should be more soluble based on the fact that they both break apart into the same number of ions. Any questions on that there? All right, so one type of experiment that really does use KSP and what we're talking about here in terms of solubility product are a bunch of experiments, like I said, that we actually don't do anymore in here. And these are what are known as qualitative analysis experiments, and you should be really happy you don't do them anymore, by the way. They are bunches of ions or groups of ions that are related to each other. For example, group 1 is silver, mercury 1, and lead 2. Group 2 are bismuth, some copper, some tin. Group 3, aluminum, nickel, all those guys. Group 4 and 5, we have some barium, calcium, sodium, and potassium. These are groups that are not related to each other based on the periodic table groups, but they are groups that are related to each other based on solubility properties. So they have very similar solubility properties. For example, silver, mercury 1, and lead are the 3 exceptions on the solubility table for chloride, bromide, and iodide. So normally chloride, bromide, and iodide are soluble in everything except these 3 ions, which means that we can separate out these ions from the other bunch of ions that are there by using what is sometimes referred to as a precipitating reagent. And the case for group 1 is actually HCl. And in this case, the HCl is actually providing chloride. So when you would do a precipitation like this or an experiment like this, and you wanted to get group 1 out of your beaker, and you had a mixture of, say, group 1 ions, 2, 3, 4 ions in there, you could add HCl, and that chloride will react with all those group 1 ions and precipitate them out. This is essentially selective precipitation like we just did in that last example. Here, you would precipitate out all the group 1 ions. Chloride is going to do nothing for the other ions in those groups, and they're going to stay in the actual solution floating around. And that would then allow you to, for example, the centrifuge off the liquid, keep the solid you then could go separate out each of the individual ions in group 1 and do some tests for them. Then when you come to group 2 and group 3, you have still in your beaker group 2 and group 3 and also group 4. Group 2 and group 3 are actually separated out from each other by the same reagent. They're actually precipitated out by hydrogen sulfide gas, which if you ever smell sulfur is a great reason why we don't want to do this anymore in these buildings. But they both use the actual same precipitating reagent, which is actually sulfide in this case. And the difference here as to how we can actually get just group 2 to precipitate out and not group 3 is we actually use what we talked about earlier, pH difference. So when you want to separate out group 2 from everybody else and not take group 3 with it, you actually make the solution really, really acidic, like a 0.5 pH, really, really acidic. And what that does is it actually is the right conditions for group 2 to precipitate out with the sulfide, but not group 3. So again, by using pH, you can selectively precipitate out one group of ions and leave the other one still in the solution. Once you get group 2 out of the way, you then can actually just turn the thing basic, really basic in this case, and like a pH of like 10-ish or something like that, 9 or 10. And now that's going to be the right conditions for group 3 ions to precipitate out, again, using the exact same precipitating solution. So as we mentioned before, things like pH is important. It will allow you to selectively precipitate things out. The concentration of your precipitating reagent, also really important. And when you get down to group 4 and 5, you have a lot of things that are soluble in everything, which means you really cannot precipitate those guys out typically. So a lot of times we do things like flame tests and stuff like that to try to identify what ions are in solution. There are certain things like barium, calcium that you can still precipitate out, but a lot of times we rely on sort of flame tests. So when you do this sort of experiment, which again, you'll never do because you're taking this class, so you never do it. Means that you really do this in order. So you want to get all group 1 out of the way first, then you want to selectively precipitate out group 2, you want to selectively precipitate out group 3 and 4. And that's really what qualitative analysis experiments are. It's just a bunch of selective precipitation, taking out each ions as groups of ions one at a time. And that way you can separate out each of the ions that are floating around in the solution. Any questions on that there? That's what you would look like if you were doing it, but probably not. That's a flame test, which everybody loves to not do. All right. Let's then talk about the next type of equilibrium, which is equilibriums for a complex ion. And for a complex ion, such as this one here, we typically will have a metal in the middle. And attached to this metal are going to be a bunch of Lewis bases, which are known as ligands. And if you remember, a Lewis base is something that does what? It donates a pair of electrons. Yeah. So again, not protons or anything like that, but we're going to donate a pair of electrons. Things that are negatively charged, things that are polar and have non-bonding electrons are good Lewis bases, like chloride here. It's negatively charged. It actually has electrons to give. So it will set up this equilibrium here. Cobalt will basically be in the middle. It will have all 4 of those chlorides attached on at some point. And overall, this thing is going to have a -2 charge. That's because the cobalt has a +2 charge, and each of these chlorides are -1. So obviously -4 + 2 is -2 overall in the charge here for our complex ion. This will set up an equilibrium. And because it does, you can write a equilibrium constant for it. And that is like every other equilibrium constant we've talked about, which is products over reactants. Again, we're still obviously using the coefficient as our exponents here. This K value is what is known as Kf. It is the equilibrium constant for a complex ion formation. As the value of the Kf increases, the stability of your complex ion also increases. And that's for the same basic reason. Because K is a large value, we should mainly have products, which means we mainly have some complex ion formation. Now, this is almost like the extreme to what we talked about with KSP. And KSP was really, really small values of K. KF is actually the other extreme. KFs are really large values. So typically, KFs are really large values that you see. And again, that's very different than what we see with KSP, which is typically the opposite, really, really small. What that means is, as we'll talk about, because they are typically very large values of KF, that means product formation is basically favored. It wants to make that complex ion. So the formation of that complex ion or making that complex ion is definitely kind of favored in the case with KF because we typically do see a large value for K. Now, what are some common ligands? Things like I said before, which have polar and have non-bonding electrons. So things like water is a really good ligand. It's got those non-bonding electrons there it can share. Something like ammonia, also a pretty good Lewis base. It's polar and also has some non-bonding electrons. Like we just saw there with chloride, something that is negatively charged means that it has gained electrons and obviously has some electrons to give. And the number of ligands that are actually attached to the metal, and usually in a complex ion, as we'll talk about in more detail in a later chapter, usually the complex ion is a small metal with a large positive charge. A lot of times it's a transition metal that's in the middle. And the number of atoms that are directly attached to it is known as its coordination number. So for example, if we take our cobalt example, it has basically 4 chlorides attached. Its coordination number is 4 in this case because it has 4 atoms directly attached to it. Now, sometimes people misunderstand this and they think, well, it's always like that number right there. And in the case of cobalt with water, water would actually attach to the oxygen here. I squeeze them all in there. Try to squeeze one more. And if we count up how many atoms, which are really the oxygen in this case, are directly attached to that metal, 1, 2, 3, 4, 5, and 6 oxygens from each of those water. And again, that would be the coordination number here. But it is not always, as I mentioned here, it is not always that number that you see. It is in the case of something like water, chloride, and ammonia. These are what are sometimes referred to as being monodentate. And monodentate ligands mean that they basically attach only in one place per molecule. So obviously chloride only has one atom, so it can only attach in one place. In the case of water, even though there's 3 atoms in water, it's going to attach only through the oxygen, and that's going to be the actual attachment point. So for example, if we took, say, cobalt with some oxalate here. We got 2 there. And let's see, let's go with we got 2, so -2. We're gonna do that. So let's say we have this complex ion here, and this is again our cobalt in the middle, and we actually have oxalate attached to it. Now, in this particular case, though, oxalate looks like this. If you're not familiar, it looks like this. And oxalate is different than, say, chloride or water. It is what is known as being bidentate, and meaning that it can attach to a metal in actually 2 places per molecule. It's those single bonded oxygens that could actually attach. So if we were to kind of just draw our oxalate over here with our guy here, I won't draw the electrons this time. Let's do that and this. It's going to attach here and here, but then we have a second oxalate, which looks like this. And this guy will also attach there and there through the single bonded oxygens. So what this means is when we look at actually this situation here, there's 1 oxygen, 2 oxygens, 3 oxygens, and actually 4 oxygens that are attached directly to the metal. That means that the actual coordination number here for this guy is not 2. It would actually be 4 in this case because of that. So again, sometimes people, when they see a formula for a complex ion and they're asked, for example, what is the coordination number? They sometimes think it's always the subscript on the bottom. It is if the ligand is monodentate and can only attach in one spot. But if it's bidentate, there are some ligands, as we'll see again in a later chapter, that can actually bind in like 3 places, 6 places per molecule. So it does depend on sort of the ligand that's present. Any questions on that there? Now, speaking of these ligands, they actually do attach one at a time. So if we go back to this previous one here, get rid of that there. Now, although this right here is the overall reaction that's basically happening here, each of these ligands actually add one at a time. So it actually happens sort of in a stepwise fashion, similar to what happens with hydrogens when we lose hydrogens in diprotic acids or triprotic acids. They come off one at a time. Here, the ligands actually get added one at a time. So what actually would happen is 1 cobalt ion would then hook up there with a chloride, and it would make an equilibrium of COCl in this case plus. And there would be a K value associated with that as that's an equilibrium. Then what would happen is this guy that's ready picked up 1 chloride will then pick up a second chloride. And this is going to give you your COCl2 in this case. And there would be an equilibrium for that. Then what would happen is this guy that's already grabbed 2 will grab a third one, setting up an equilibrium COCl3, and now we're going negative here with our charge. And there'd be a K value for that. And lastly, this guy here would pick up the last chloride in this case. Again, making the complex ion that we see there with a -2 charge and a K4. So this is the stepwise sort of way that ligands get attached in this case. And again, they do get attached one at a time. They do set up an equilibrium one at a time, and there is usually like an equilibrium constant for it. This is really no different than what we talked about when we did equilibrium. If I wanted to add all 4 of those reactions together, what's going to happen is this guy and this guy is going to cancel. This guy and this guy is going to cancel. This guy and this guy is going to cancel. And what that's going to leave you is I got a cobalt ion that added 1, 2, 3, and 4 chlorides to make my complex ion in this case, right? Now, if I wanted to get the Kf for this guy, what do I do with all these K values? Do I add them, multiply them, divide them? When we add reactions, K values get multiplied. Yeah, so if you wanted the Kf here, you would multiply all those K values basically together. Any questions on that? So sometimes in these problems with KF and complex ions, sometimes they'll give you the overall reaction that happens when all the ligands have been added. Sometimes they may give it to you in a stepwise sort of fashion here, where you could kind of put all the steps together and get the overall reaction that's happening along with the K value associated with that. Any questions on that? All right. So let's take a look at one here together to sort of talk about the special sort of things that we do when we're dealing with these type of calculations. So there are a few things that we do because it is a large value of K and because it is sort of a complex ion being formed. So in this particular case, we want to know if we take 0.2 moles of copper 2 sulfate and we mix it with a liter of 1.2 molar ammonia, what is the concentration of copper at equilibrium? Just for this example, and not always the case, but just for this example, we're going to assume all the volumes for everybody just stays at 1 liter. So we're just going to kind of make that assumption. It's not always the case, but here we could kind of then get an idea what's going on. So we are going to do an ice table, and we do want the concentration of copper, and we do want the concentration of ammonia to be when everybody's mixed together. And in this particular case, this copper 2 sulfate is our source of copper 2 in this case. So initially here, we would have 0.2 molar, and again, we're just going to assume everybody is 1 liter. So obviously 0.2 moles divided by 1 liter will give us 0.2 molar for our copper in this case. Yeah. For our ammonia, it's going to be basically 1.2 molar in this case. And we're going to have 0. So you do need to do an ice table like normal. Now, if we were going to do this sort of ice table like normal, and again, we typically would do it in molarity, we would then normally, and I'll do this in blue, we would normally go through this and do a minus x, right? A minus 4x, and we would do like a plus x on this side. So that's normally how we would do it. But this is where one of the assumptions that we do in these type of problems come into play. And that again has to do with our KF value. Because the KF is large, we can assume that in this particular case, all of the metal will get used up in the complex ion. So because we have a really large value of K, we will assume that pretty much that complex ion is going to want to be formed, and all of this copper is going to end up over here in this complex ion. So what we typically do in this case is, because we make this assumption, we actually don't really do the X's in this case. We do the actual concentration of the metal. So this would be minus 0.2, which is the concentration of our metal. This would be minus 4 times 0.2. Why did I do the 4? The 4 is still like our 4x, right? So we need the coefficient there to have the right mole-to-mole relationship. This would then be plus 0.2. Again, nothing on this guy or this guy because really the coefficient is 1, right? So that is basically, this number here is basically in this case x, right? And that is the assumption that we're making in this particular case. At this point, we're going to carry everybody down. We're going to get 0 here for our copper. We will end up with 1.2 minus 4 times 0.2. I take my scientific notation off. That's going to get us a 0.4 molar, and we'll have a 0.2 molar at this point. First off, any questions on that ice table? So kind of different here. We assume that in this case with KFs, because they're typically large, that all the metal should be the one that gets used up, should be the change, and that should end up in the complex ion. Now, because we made that assumption, we do have to make sort of a second assumption in this case, which is if we think about the question is how much copper-2 do we have at equilibrium? And clearly here we zeroed it out because we use that as our change, which means if that was the answer, there wouldn't be much to do, right? So it's not going to be 0. So the second assumption that we make is although almost all of it should end up, all of the copper should end up over here in the complex ion, this is still an equilibrium, which means the reaction heads not always in one direction. It does come back in the other direction a little bit. So even though almost 99.99% of all the copper is going to end up in that complex ion, there will be just a bit of it heading back that way. And we should end up with a really small concentration of our metal at equilibrium. So even though we kind of assume it all ends up there in the complex ion, some of it is going to come back the other way. So how do we do that? Well, we could actually use X now to represent really our equilibrium concentration of our copper. And we could use our KF expression, which is our products reactants. And again, don't forget for our NH3 here, we do need to take it to the 4th because of the coefficient. That's going to equal 5.0 times 10 to the 13. So we basically have this concentration. We have this concentration. That guy is basically our unknown. So we could actually solve for the copper concentration. And if you do that, these two guys basically just switch partner places. So that would give you the copper concentration is going to equal our complex ions concentration at equilibrium divided by our KF value and our NH3 once again to the 4th. So now putting our numbers in, we end up with 0.2 divided by our KF, which was 5.0 times 10 to the 13, times our NH3 from equilibrium, which is 0.4. And again, we still need to take it to the 4th power. So if we do that, we end up with 0.2 divided by 5 to the 13 divided by 0.4 to the 4th. That is going to give me a copper ion concentration at equilibrium that equals roughly 1.6 times 10 to the minus 13 molar. Is that concentration a large value or a small value? That's a super small value. It pretty much validates our second assumption of pretty much all the copper is in the complex ion. I mean, you got barely nothing left still freely floating around in that solution. Now, if you did this calculation and you ended up with a large value for copper, you screwed up. Yeah. So that's something to think about. Yeah. So you definitely should not end up with a large calculation. Put the phone ringing. Like, I don't know if I've heard that ring for like ever. What the heck, the weird fire? All right. Any questions on that? All right. So like I said, you should definitely always in these type of problems pretty much hit a very small value for the concentration of our ions at equilibrium. And again, if you hit a large value, you're going to end up probably messed up somewhere along the way. All right. So why don't you try one here, which is this one. Here we want to calculate the concentrations of everybody here. The silver ion concentration, an intermediate, our complex ion. if we actually mix together 150 milliliters of 1 times 10 to the minus 3 molar silver nitrate with 200 milliliters of 5 molar Na2S2O3. Here they do give you the KF in a stepwise fashion here to see what you come up with. We're not assuming the volume stays constant. This one is a little bit different than the previous one. Again, we're not keeping any volumes constant. Also, we're given not really the overall sort of reaction that's happening, but we're given the stepwise formation here of this complex ion. So one of the first things we could do actually, if we wanted to, is just take these two reactions and we could add them together to really get kind of the overall reaction that's taking place in this case. In this case here, this sort of intermediate here will get canceled, and that will leave us basically here we have a silver ion plus 2 of the S2O3 2 minuses going to give us our complex ion at this point. And in this particular case, the Kf would equal the K1 times the K2. Again, here we don't add the K values when we add an equation, we do multiply them. So if we did get that value, which in this case would be, we'll call it 2.9 to the 13. So in this particular case, we may want to focus in on the overall reaction, as it can allow us to calculate a number of these guys here, since in this case, we do want to pretty much figure out everybody's concentration along the way. We could kind of focus on the overall sort of reaction that's going to happen when everybody mixes together. With that being said, we do need really the concentration of each of these things after they've been mixed together. The silver nitrate here is going to be our source of silver, while the Na2S2O3 will be our source of the S2O3 2 minus. The thiosulfate there will be our source of that. So our total volume here basically is 150 plus 200 milliliters, and that's going to give us about a 350 milliliter total volume. So for the concentration of silver, because in our silver nitrate, it is a 1-to-1 relationship between how silver nitrate breaks apart, the concentration of this guy will be the concentration of that guy. So we could just use the 1 times 10 to the minus 3. So go 1 times 10 to the minus 3 molar. We are using 150 milliliters of it. We're basically doing our M1V1 equals M2V2 here. M2 here would then be our total volume, V2, which is our 350 milliliters in this case. Solving for M2, that will give us our silver concentration. And that's going to get us here for the silver, looks like basically 4.29 times 10. Looks like 1, 2, 3, 4 minus 4 molar. We're going to do basically the same thing for our S2O3 2 minus. This here again is going to be the source of it. And when that guy breaks apart, you get 2 sodiums and 1 of these guys. So once again, it is a 1-to-1 relationship between those two. So we could use, again, the concentration of 5 molar for just the ion as well. And that would get us here, once again, doing M1V1 equals M2V2, 5 molar times 200 milliliters used of that guy equals our M2, and once again, our total volume here of 350 milliliters. That's going to give us 5 times 200 divided by 350. We'll call it 2.86 here. Any questions on that part there? Now that I have kind of the concentrations here of the silver and our S2O4, we can then use the overall reaction to really start getting some of the answers we're looking for. So let's do that. I'm going to flip the page here so I got more to write with. So taking our overall reaction, which is our silver plus 2 of these guys, give us our complex ion here. We're going to do our ice table. So we're going to use the concentrations we just calculated. And that was for this guy here, 4.29 times 10 to the minus 4. For this guy, it was 2.86. And for this guy here, it is 0. Since, again, this is our complex ion formation and our Kf value, which as we calculated was like to the 13th, is a large value. We're going to make our assumption like we did on the first problem. Metal, which in this case is the silver ion, should get used up. So that is going to be our change. It's going to be minus 4.29 times 10 to the minus 4. And again, this is molarity we're using right now. This is going to be minus 2 times 4.29 times 10 to the minus 4. Again, remember, this is the same as like minus 2x. So you got to have that 2 in there to get the right sort of stoichiometry. This will be plus 4.29 times 10 to the minus 4. That means at equilibrium here, we got 0 of our silver, like we would anticipate because we assume it's all going to get tied up in that complex ion. We do our subtraction here, and we actually still end up with basically 2.86. And here we end up with 4.29 times 10 to the minus 4 molar. First off, any questions on that ice table there? At this point from this ice table here, we've actually answered a couple of questions that it was looking for. We have the equilibrium concentration of S2O32 minus, and that is 2.86 molar. We have the equilibrium concentration of our complex ion, which is 4.29 times 10 to the minus 4 molar. At this point, there are a couple of things we were still looking for. So I think we got this guy. So we're still looking for these guys' concentrations. So at this point, you really do have a couple of options of what you could do. So because they gave us each of these equilibriums reactions separately, you could actually use each of them separately if you choose to. And why I might want to do that is if I look at what I just got from this ice table, I have this guy's concentration and I have this guy's concentration, which means I can use my equilibrium expression and actually figure out that guy's concentration from it. So that is what I'm going to do. I'm going to now use K2 reaction here to basically figure out our missing guy here. So if I wrote my K2 equilibrium expression, it would be my complex ion divided by this guy here, which is our intermediate that I'm actually looking for, what its concentration is, times S2O32 minus. And that's going to equal my K2 value here of 3.9 times 10 to the 4th. Now you may be asking, how come I did not square that one? I did not square that one because I am not doing this reaction. I am doing this reaction, right? That is also why I use this K value, which goes with this reaction, and not the overall K value. Yeah, so that is why I'm using those guys. At this point, we basically have this concentration, this concentration. So once again, these two guys are just going to switch places, basically. We're going to multiply the guy on the bottom to the other side and divide. And we will end up then with what we are looking for, which is this intermediate here, will equal our complex ion divided by our K2 in this case, and our concentration of S2O32 minus. So putting in our actual numbers, that's going to give us 4.29 times 10 to the minus, what do we get there? 4. Divided by our K2, which was 3.9 times 10 to the 4th. And our S2, which is 2.86 in this case. So doing all that good stuff there will give us 4.29 to the minus 4 divided by 3.9 to the 4th divided by 2.86. And that's going to get us here. I'm going to go scientific notation. So I'm going to end up with maybe a 3.8 times 10 to the minus 9 molar. If you're not in scientific notation, your calculator probably has a bunch of zeros and a 4 at the end. Yeah. And that's just because it ran out of room. So that's okay too if you got the 4 there. Any questions on that one there? Yeah. Yeah, it's for the S2O3 2 minus concentration. Yeah. What's that? Are we talking about where? You good? Yeah. Yeah. So that's this guy's concentration, which is basically this guy's concentration. And since these are all equilibrium, it's actually this guy's concentration as well. So that's where that comes from. Yeah. And actually, in that case, when we subtracted, it really didn't change the concentration very much because it was a very small number that we were subtracting. So what it kind of started with is what it ended with. Yeah. Other questions? All right. So now that I kind of used the second equilibrium there to figure out this guy's concentration, I again have another option as what I could do, but probably the simplest thing would be at this point, I now know this concentration. I still know this concentration. I could actually now use the first equation here to figure out silver's concentration. So that is what I'm going to do next is I'm going to use the first equilibrium expression and equation along with the first equilibrium's K value to figure out my silver. And if I do that there, let me just rewrite that there as 2. So we basically have silver plus S2O3 2 minus. And again goes to what we got there, AG S2O3. And in this case here we have 7.4 to the 8. All right, so we can again use our equilibrium here for our K1, which would be our product divided by our reactants. And once again, because we're using the actual first equilibrium reaction here, we are not squaring anything or anything like that. And this would equal 7.4 times 10 to the 8. So we're going to use our values we just calculated. So 3.8 to the minus 9 for our top guy. We are looking for the silver's concentration at this point. And once again, we still have 2.86 for our S2O3, 2 minus equals 7.4 times 10 to the 8. Once again, these two guys are basically just going to switch places. And that would give us a silver concentration that equals 3.8 times 10 to the minus 9 divided by 7.4 times 10 to the 8 and 2.86. So popping those numbers in, we end up with and by the way, our answer for our free silver ions should be a large or small value. Should be small, right? Our assumption is it all gets used up. And if you do that, I think this qualifies 1.8 times 10 to the minus 18 molar. That is, as they say, quite small, yes? So again, this validates our assumption that pretty much all the silver in this case is going to be used up into that complex ion. And this demonstrated that we had our stepwise formation and you could use each of those individual sort of equilibrium reactions separately because they're all equilibrium as long as you have the equilibrium constants for our concentrations for everybody. Now, just to show you, you could have took just a different approach a little bit. You could have, after this first ice table here, you could have absolutely done what we did in the first problem, which was go after the silver first. So because we got the K value originally, which was 2.9 to the 13, you could have done what we did in the first one, and I'll just bring it back over here. Actually, I'll do it right here. You could have done your KF would have been your complex ion divided by your silver concentration and your S2O32 minus. This one you would need to square because we're now using the overall reaction. So you would need to actually square this one. And this would equal our 2.9 times 10 to the 13. Putting in our numbers here, this would give us 4.29 times 10 to the minus 4 divided by our KF as these two guys switch places. So that will give us 2.9 times 10 to the 13. And our 2.86 squared would equal our silver concentration. And if you pop that into your calculator here, you end up with 1.8 times 10 to the minus 18 molar. So again, you could have absolutely kind of done it like we did on the first one, go after the silver first. And then what you would probably have to do at that point, if you did that, is use K1, because now you'll have the silver, you'll have this, and you actually then could use K1 to solve for that guy and go that direction as well. So again, there is some variability in terms of how you want to attack it. But as long as you use any of those equilibrium ones, they all should end up basically this here. And finish this up here. We've got one more little thing here to talk about. So obviously, as we've seen here, there's a couple different approaches here to these KF type problems. Again, typically the two things that you want to think about is you want to make sure you have the concentration of everybody once it's all mixed together. And again, those two sort of assumptions that we make, which is because the KF value is relatively large, we do assume that all the metal gets tied up in the complex ion. That also gives us really the changes that's going to occur. And secondly, when we actually do go back and solve for the concentration of the free metal ion that's floating around that solution, it should be, again, a small value. And that's a good way to check. Again, if you get a large value, probably, like I mentioned before, something did not go so right there. Let's take a look at one more sort of example here, which is this one here. We want to calculate the molar solubility of silver chloride in 1 molar ammonia. They actually give us two equilibriums here. So we have our silver chloride, which is insoluble, and we have a KSP sort of equilibrium. And we also have the complex ion formation, which is our KF. So in this particular case, we can still sort of approach it similar to what we did in the previous ones. Here we can actually add together these reactions like we've done before and really kind of take a look and see what is going on overall. And in this particular case, what you will actually see is the silver ion is actually going to go away. And we will end up with silver chloride plus some ammonia here. Going to make our complex ion. And some chloride in this case. Now we could get the K value here by taking the KSP and timesing it by the KF. Now, sometimes people wonder, well, they are different Ks in a sense, but it doesn't really matter because ultimately they're all just equilibrium constants. So it doesn't really matter if they're KA, KB, KW, KSP, whatever K we got going on. They're all basically the same thing. And it's the same idea as when we do like Kw equals Ka times Kb. So it all works out the same. So in this particular case, if we do that, we got 1.6 to the minus 10 times 1.5 to the 7. That's going to give us a K value here for the combined reaction of 2.4 times 10 to the minus 3. Now, at this particular point, what you should probably see is we are looking for molar solubility, which is the molarity, right? Moles per liter. And in this particular case, we actually end up with a small value of K. And that's because here we're not going to do really a traditional sort of KF type calculation. Because we are looking for solubility, we're actually going to do a more KSP type calculation here because that is what we're looking for. So we'll take the overall reaction here again, which is our silver chloride plus our 2 ammonias, giving us again our complex ion there and our chloride. With our K that we calculated there, which was 2.4 to the minus 3. So in this particular case, we're going to do a similar ice table to what we do with solubility. And here we do have one piece of information given to us, which was the molarity of the ammonia. So we do know the molarity of the ammonia is 1. So we actually do have an initial concentration here on the left. The rest of it's going to be very similar to a KSP table. So we're going to do some zeros. The change here, although normally in a KSP we don't have anything on the left-hand side, this case we do. This would be minus 2s, again, for the coefficient. This would be plus s and plus s. This means at equilibrium, we will end up with 1 minus 2s, s, and s. Any questions on the ice table here? Now, just like normal, this is going to go into our equilibrium expression, and it is a little bit different than normal KSP because we actually do have reactants. So this will be our complex ion times our chloride divided by our NH3. And once again, we do need to square it because of the 2. This obviously is a solid, so even though we are going to sort of relate it back to it, we don't really do anything with it in terms of the ice table. So we're going to put our numbers into here, and that's going to give us basically s squared up on top. It's going to give us 1 minus 2s squared on the bottom, and that's going to equal 2.4 times 10 to the minus 3. So like normal here, we do want to solve for S, which is the molar solubility. And hopefully you could see the easy way to do it, which is just a big old square root on both sides, right? So it is a perfect square on both sides. That's going to give us an S on top, a 1.0 minus 2s on the bottom. I don't want to forget to do, which is actually take the square root here of 2.4 to the minus 3. Going to give us a 4 point, and we'll call it 90 times 10 to the minus 2. We're going to multiply this to the other side. That's going to give us an S is equal to 4.9 times 10 to the minus 2 minus basically 2 times that, 9.80 times 10 to the minus 2 S. We're going to combine our S's, so I'm going to bring my S back over this way. Once again, kind of like what we did in our buffer calculation, that is a 1, right? So we're basically going to take that plus 1, and that's going to give us a 1.09, and we'll call it 80S equals 4.90 times 10 to the minus 2. Dividing now to the other side, that is going to get us something like this of a molar solubility of 4 point, we'll call it 4.6 times 10 to the minus 2 moles per liter, or the molar solubility here. Any questions on that calculation there? Now, just for comparison of what we did before, if we were going to turn that into grams per liter, we would take 4.46 times 10 to the minus 2 moles per liter. We would use the molar mass of silver chloride from the periodic table, 143.35 grams per mole. So that would tell us that in this particular case, we would end up with about 6.40 grams per liter will actually be soluble in the ammonia. Now, we actually did the solubility of silver chloride earlier on in this chapter, and that would give us basically S squared is equal to 1.6 times 10 to the minus 10, square rooting both sides would give us a molar solubility of silver chloride in water of what we saw earlier, which was like 1.26 times 10 to the minus 5 moles per liter. And if we times that by our 143.35 grams per mole, that would give us for water a solubility of, as we saw earlier, something like 0.0018 grams per liter. So between water, which is 0.0018 grams per liter, and the ammonia, which one is it more soluble in? It is definitely more soluble in the ammonia. And that's because the formation of a complex ion is way favored than not being there. So when those ligands get near something that can form a complex ion, because the values are so large for Kf, it is definitely favored. In fact, if you did those sort of qualitative analysis experiments like we talked about, you actually, in the process of doing group 1, you make a silver chloride solid, and then basically you add ammonia to it, and the solid basically goes away. It is that much favored that the ammonia is able to rip apart the silver and the chloride from each other. So the silver can then go and basically make a complex ion. You could actually then get it back because you have chloride there. You could make it more acidic, which will change the pH, and get rid of the ammonia, and you actually will see the solid come back. And that's actually how you test, for example, for silver's presence, is you make the silver chloride, you get rid of the silver chloride by adding the ammonia to make this complex ion, and then you make it more acidic, which will then bring the silver chloride back in that solid. And again, the formation of a complex